Windows laptop with security cameras, not a very good idea.
What could go wrong?
Make sure I get my VPN turned off real quick.
Once I get started, I won't be able to test it.
Just going to give it about another minute or so for people to filter in and get started.
They didn't need you? Oh.
So, good morning, everyone.
Good morning.
Yay, some of you are live. That's always good. So, thank you very much for coming out. This is actually my first time in Kentucky. I'm from Cleveland at Hurricane Labs, and I'm our Director of Technical Operations, which basically means these days is that to quote Office Space, I take the requirements from the customers and I give them to the engineers. Used to do a lot more technical work on our network side and did some Splunk administration. Now I get to be the person who's basically responsible for making sure that all of our customers' work is done and that they're happy. So whatever technical or managerial things that need to be done are something that I get to do. So it's very rewarding and something I enjoy doing. On the topic of something that is a very fundamental part of how computers and how the internet works, but also something that's very, very interesting from a security operations perspective. I'm going to be talking today about the domain name system, DNS. As part of this talk, I'm going to occasionally make some jokes that are pretty bad, which is kind of my trademark. So I appreciate if you laugh for those. Does anyone bring any tomatoes to throw? No? Okay. Well, I got some. Just if anyone, yeah, I can't even. We'll just kind of roll these down the center aisle. If anyone wants to make sure, if you're offended in any way, just I'm going to hit one person in the center. Here, I'll throw a couple in the back. Somehow I'm going to set off the sprinklers in here, but it'll make the talk more exciting. But as John mentioned in the keynote just before this talk, metadata is very important for security intelligence. And really, I think that DNS could be already it's happening. That's great. Love an audience that's alive. So as John mentioned in the keynote, metadata is really important. And I think that DNS is really one of the most interesting and most useful forms of metadata. Almost the ultimate form of metadata. And we're going to dive into how DNS works so that everyone can understand that. It might be review for some of you, but it might not be. And really the goal of when I wanted to write this presentation was I found myself on like a very regular basis trying to explain DNS to people and finding that people who were DNS administrators often didn't exactly know how the technology works. I really hope that doesn't apply to some of you in this room, but if it does, that's fine. You're going to leave here knowing a lot more about how DNS operates. And really, I want you to leave here with more knowledge about something that's really important to the operation of the internet than you came. So if that is what happens, I've done my job. So let's get started. Assuming I can figure out how to use a laptop. So why are we talking about DNS? Well, name resolution is obviously important when it comes to using the internet. How many of you here have had this question posed to you? Is the internet down? Some of you have had people ask that to you, of course. It almost makes me think of back in college, I was in an apartment complex and all the internet was not working except for mine. And all my friends are like, calling me and it's like, hey, the internet's down. I'm like, no, it's fine. What actually happened is the provider, the ISP for that apartment complex, was having a denial of service attack on their DNS servers, and they were down. I was running my own DNS server, going through the DNS process that we're going to talk about. I didn't notice anything. My name resolution was fine, and my internet was working great. Everyone else was just out of luck because they weren't using another DNS provider. So, users really don't like it when you call the help desk. They're like, yeah, the internet's down. No, the internet's fine. We're just not having DNS resolution. Go to this IP address and you'll get the website. It doesn't work that well. So, people expect name resolution to be the same as the internet working. Also, I really, really like everyone to know how things work. If we're running something, if we're administering something, I want us to be able to not only be able to keep that running, but be able to have some competent understanding of how it functions. And that's really my goal, to be able to understand and explain to someone how the internet or how DNS works. And then, since this is a security presentation, I want to talk about how DNS can be used by hackers. Because it's such a ubiquitous part of how every network functions, attackers love to use it for very evil things. And it can be definitely something that's leveraged, and it is being actively leveraged in a number of attacks. And finally, where we get into the metadata side of things, security intelligence. And this is really the cool and interesting part of DNS. We're going to start by understanding how it works, we're going to understand how attackers use it, but then we're going to look at what we can do as security professionals to leverage DNS data to either better secure our organization, to protect against potential attacks or investigate attacks, or also to just get a better sense of what our users are doing and what our machines are doing, and forensically investigate what's happening. So let's get started in talking about the DNS structure. DNS is actually the best example of a database in the world that's globally distributed. How many of you either currently or now run a database or function as a DBA in some functionality or something? At least I saw one hand. How many of you at least understand the idea that databases can be a pain to administer? Yes. So the fact that DNS works is amazing because you have not just one database, but everyone across the world that runs a DNS server is a part of this database. And there's no single source of information. This database is distributed across the world. In terms of DNS technology or terminology, there's a lot of different types of DNS servers and different DNS terms. So we have the concept of a local resolver. That is your DNS server that lives locally on your network. It's typically your DNS server for your organization. It might be a domain controller. That's where your users are going to be going locally for getting DNS. We also have public DNS servers, which if your local reserver is poorly configured, it might be a public DNS server, and that can be bad, and we'll talk about why. But those are typically provisioned by ISPs or other providers, the best example being Google's Quad 8 DNS server. Caching is a technology or technique that's used by DNS in order to reduce the number of queries. Basically, every time something needs to resolve a name, there's a lifetime or a time to live on that, and that cache reduces some of the traffic on the internet as a result of that. Root servers are at the top of the DNS tree, which we'll talk about very shortly. They do not provide every bit of information about every domain name. They only know where the top level domains are, and that's a common misunderstanding. But root servers can get you to the authoritative name servers, and that's what we would run if you were running a domain. You would have the authoritative domain server for that name. Now, the way I like to explain DNS is a tree. And you want to look at it from the right to the left. And basically, it builds on itself. So at the top of every DNS name, or the top of the tree, is this invisible dot here, the DNS root. You don't type that, but it's implied. And if you've ever configured a DNS zone file, you know how important periods are. So when I was a grader for a DNS class in college, there was the first lab report where I ended up taking a point off for every period that was missed in the write-up of the lab report. And people were telling me like I was a horrible person and a jerk for doing this. I'm like, guys, when you get to zone files, you'll understand why periods are important. And then they appreciate it, I think, at least. But at the top level, you have the top level domain servers, your .com, your .org, your .info, all of those. So tree, root, top level. Off of every top level, you have individual domain names that are delegated from the top level domain. So your Hurricane Labs, your Google, all of that. And then individual domains can delegate subdomains as they need them. So basically, each level controls the next level down. So at the top level, we know how to get to Hurricane Labs, and then Hurricane Labs can control everything that's a subdomain of Hurricane Labs. So I want to walk you through what a DNS request looks like and the process of resolving it all the way to the DNS root, so that you'll be able to walk through how that works. So let's just say that there's a client server that wants to go to hurricanelabs.com. I would recommend that every client wants to do this at some point. This client sends a request to the local DNS server saying, hey, I want to go to hurricanelabs.com. What's the IP address? The local DNS server, since no one has ever gone to that at this company, doesn't know the domain. So it wants to figure out how to get there. In fact, this local DNS server has never looked up .com before because it was just turned on and has an empty cache. So the local DNS server is going to go to the root server and say, where is .com? Where's the authoritative name server for .com? So the root server is going to look through its list of .com, .net, .org, all the top level domains, and return the address of the authoritative name server for .com to the local DNS server. That's all that the root server does. It doesn't tell you where's hurricanelabs.com. It doesn't tell you where www.hurricanelabs.com. The root server only knows about the top level domains. And that's really a function of keeping the internet working. Because if we had to update all that information to the root server, it would be completely unmanageable. And the level of traffic going to those root servers would be completely unmanageable. So next, now that we know where .com is, we're going to have our local DNS server go back and talk to the top-level domain server for .com. And the .com top-level domain server looks through its list of 4 domains, Hurricane Labs, Google, Amazon, and Facebook, and returns the authoritative name server for hurricanelabs.com to our local DNS server. We're not done yet. We only know how to get to the Hurricane Labs name server. We still have to make another request. So now the local DNS server goes.
Tommy here. Unfortunately, I have video freeze up, but audio should resume at about the 12-minute, 44-second mark.
Command. And really, this is an efficient attack because the attacker only needs to provide the botnet agents a list of open resolvers to use and a target victim. So what actually happens in this case is the attacker tells all the botnet, hey, this bad guy or this good guy, I want them to go away by launching a denial of service attack. And these open resolvers are things that I can publicly send DNS requests to. And what it actually does is all of these botnet agents will spoof the source of the attack, or spoof the source IP address to actually be this victim server. So whatever this IP address is, that's where all these botnets are going to say traffic is originating from. So that traffic is going to be a DNS request, often a DNS any request, which has the largest return payload of any DNS request. You could also do it with other DNS requests, but you're not going to get the same effect, because you really want to create as much return traffic as possible for the smallest amount of incoming traffic. And basically, we're sending to all of these open resolvers a, hey, list me everything that you have and throw it at this poor guy. So inevitably what's going to happen is all of these DNS servers with a lot of bandwidth are going to be sending tons of unsolicited return DNS traffic to this victim server, knocking it offline. So really, these misconfigured systems contribute to this denial of service attack. So if you have an open resolver, you can be part of a denial of service attack, not on the botnet side or on the attacker side, but as a contributor to the amount of traffic that's coming in. So at this point, you're probably wondering, how do we stop this? And really, proper configuration is the way to do that. Unfortunately, on the front of every DNS server is a switch that you can use to turn off recursion. You just press that and you're done. But it's actually a config file change. So you need to allow different domains that you own to be resolved, but you don't want to allow recursion to be allowed. So it's really a simple configuration change depending on if you're running Bind or Windows for your public-facing DNS. You could do the different configuration. But it is a simple change. And as long as you correctly define the domains that you're owning, it'll be something that you can do. And really the thing to remember for this is that you are not an ISP unless, of course, you are. So you don't want to be the nice guy on the internet here that goes ahead and looks up domains randomly that other people ask. Because you only want to provide responses for domains that you own. Other things that we can talk about. Blind transfers. These are something that are bad. A name or a zone transfer is a fundamental operation for a master and slave DNS configuration, where we have one system that is the authoritative or the master source of information, and you want all of the other DNS servers in your organization to stay in sync. It's expected for those to transfer information on a regular basis because they need to be in sync when anything changes. However, you don't want some random person on the internet to be able to be, hey, I'm now a name server, and I want to grab all of your domain information, please. Even if they say please, you don't want that to work. The reason that this can be used is if you're trying to do a pen test from the outside, or even inside the organization. And the first thing you want to know is what services are hosted where. So if I'm trying to look at something from the outside, and I get a list of all the domains, and say I see, intranet.yourdomain.com, there's a high likelihood that it's probably an intranet site. Same for portal or mail. You already know what things are without having to do any sort of scanning. So like if you're a pen tester, that's one of the best tools that you can use to quickly get information about an organization, about what systems are valuable or vulnerable, without having to do any sort of network scanning. It's just another tool that you can use. So without having this information, it makes you do a little bit more work. Not a lot more work, but it's at least something that makes it not as obvious. The next kind of attack that we can see is the idea of domain hijacking. And this has been leveraged in a couple of high-profile attacks. New York Times being a great example. Basically, this is a pure social engineering attack, where some bad guy can say, hey, I own NewYorkTimes.com, and we're moving data centers, and we're not in New York anymore, we're in Russia. So can you change all of the records for NewYorkTimes.com to point to the registrar in Russia, and everything will be cool. And the registrar's like, sure, that makes perfect sense. We'll just move all the New York Times to Russia. And the registration information is modified without your permission. So that can be an attack that is difficult to prevent, obviously, because you're at the mercy of the registrar doing their job. So one of the best ways to prevent something like this from happening is to detect for modifications to any of your registration information, and then immediately be able to contact the registrar. Or to have that domain locked so that it can't change. But even if something's locked, there's the possibility that that can be socially engineered as well. But that's definitely something that's been used in high-profile attacks for things that a lot of people are going to go to, New York Times being a great example. DNS is also an amazing covert channel because it's something that is ubiquitous in almost any form of networking, because we have to resolve names in order for the internet to look like it's working. So DNS is pretty much allowed all the time. That means that if there is something that's preventing you from going to the internet normally, like a captive portal, DNS is typically allowed and works as expected. And that will allow you to use DNS as a tunnel to transmit information out. And it's really one of the things that DNS is seen as a harmless protocol, rarely blocked, and even if DNS is something that is restricted, the way that DNS works in a hierarchical approach, you're pretty much going to be able to resolve a name to talk to another server, and that other server that you ultimately control can be used to do things that look like DNS requests but are actually more than that. So really the question is when is a DNS request more than just a DNS request? So in this case, you can have a client that's running a DNS tunnel client application, and probably one of the best and easiest to use versions of this is a tool called Iodine. The reason they call it iodine is 53 on the periodic table, and DNS is port 53. So someone was a little clever there. And basically, you can run a DNS server, a tunnel server, running the iodine server application. Your client can run that as well. And you can send a bunch of DNS requests that look like DNS requests that are typically text records. And it'll go through the local DNS server, all the way through your firewall, through the internet, and get here. And you'll be able to exfiltrate data, for example. So this is what this will often look like if you're looking at DNS logs. So let's just say I have my tunnel hosted at tunnel.shadysite.info, because every info site is shady to begin with, and shadysite.info is even more shady. Obviously, you want to make this as small as possible. So this is probably a poor domain for actually exfiltrating data with DNS, but if you want to shorten this down to like like the shortest .info domain you can find, that would work better because it gives you more room in the DNS request for payload. But basically, it'll look like this happening in your network. Random characters that are basically encoding information. And those requests will hop through DNS and make it to the destination. You can actually send data 2 ways with that. And it's really one of the most powerful ways to exfiltrate data that works almost all the time. So inevitably, you're going to be wondering, how do we stop this? And there's a lot of options for that. And as we get into the security intelligence, we can talk more about that. Initially, like looking for odd behavior and anomalies, and thresholding DNS request volumes are all options. But a lot of the security intelligence that we can do with analyzing DNS request volume can really be used for this. And that leads nicely into the final part of this presentation, where we start talking about DNS security intelligence. And this is really where we take DNS existing as this useful part of making the internet work. We understand that it's vulnerable and we understand that there's threats. But what can we do with all the DNS information in our organization to provide better security and know what's happening? And really, if there is any source of information that you want to bring in when you're doing a security assessment or looking to implement a security intelligence program, DNS is probably one of the easiest ones to get and one of the most useful. Because there's nothing else that provides the level of detail about what clients are doing in a human understandable format than DNS requests. So there's all kinds of use cases for DNS security that we're going to go through. One of the first ones is going to be SSL encrypted traffic analysis. With so many things resolving or relying on HTTPS or encrypted communication, we can't rely on being able to dig into an HTTP request because pretty much anything these days is going to be encrypted. And doing man-in-the-middle on SSL is not always practical, especially depending on how things are set up. If there's user systems that you don't control, for example, and you can't push out a certificate to them. So being able to see what's happening without having to break SSL is very useful. The threat intelligence to understand what bad actors are using what DNS names and being able to correlate requests to actual bad IP addresses. Forensics investigations of attacks, being able to find your patient zero, figure out what data was sent where, what systems they talked to, and what other systems in your organization might be also victims to that. DNS tunneling, detecting the exfiltration of data, and is DNS being used as a covert channel in your organization, or for just accessing resources that shouldn't be resourced? And then also for threat research. There's a lot of research that can be done correlating bad actors, understanding what systems are compromised or what bad things exist on the internet by using DNS. And it's really one of the best sources of OSINT that can be used as well. So to talk about SSL traffic correlation, really the problem that we see is almost everything is encrypted. This could be just our normal requests as part of web browsing, using Google, for example, using webmail. Webmail might be something that's not allowed in your organization, and you need to understand when users are doing that. Really the best solution for something like this without breaking SSL is to understand, correlate your SSL proxy logs, your web proxy logs, your firewall logs to your DNS logs. Because this gives you an IP address, your firewall will give you an IP address, DNS logs give you a host name and the associated IP address for that. So you already have a name and an IP address to know this user was doing this at this time. And you don't have to dig into trying to break the SSL in real time. Here's also threat intelligence. There are bajillions, literally, of DNS or domain name blacklists that exist on the internet. Everyone has their own blacklist. How they generate that, it's all up to the person who creates that blacklist. But if we look for DNS lookups for known malicious sites in our logs, we know that there could be clients that are going to things that are on threat lists. And we don't really have to look for other details on that. If we see a DNS request happening for something that we know is posting malware, for example, or a ransomware site or anything like that, we immediately know, okay, this client looked up this domain for some reason. This is something we need to investigate. And it's just a quick bit of information. This request shouldn't happen because this is bad. We need this information. And then also looking for hosting providers associated with ransomware. So there are some hosting providers that are notably shady, that have a lot of ransomware associated with them. And these they have lots of IP addresses that are associated with these providers. And just by knowing, hey, I see this request for this domain that resolves to this IP address. This IP address is from a provider that's known to be hosting ransomware. The fact that I'm seeing this domain that I've never seen before, but it has a high probability of going back to this provider that has this history, that's something we might need to look at as well. So using this data, you can almost see in advance that something might be bad or has a high probability of being bad without even knowing what the domain actually is. We look at it from the forensics investigation side. DNS can provide a lot of information about the timeline of an attack. Walking through, okay, this client looked up this domain, and now, as we saw actually in the initial presentation for the carbon black presentation, where we saw the pull to GitHub, for example, that was in the demonstration, we see that there would be a DNS request for that. We might see DNS requests to other systems, and we might, after we see that happen, we might see other clients starting to make those requests. And you can really walk through, okay, this was the first client that was compromised. It downloaded this executable from this domain. Now we see another system going out to that domain and pulling down this executable. Now we see requests going out to this other site. A lot of requests that might be a DNS tunnel, for example, where they're exfiltrating data. And really just using DNS combined with our other logs that we have to understand what's happening. And you can also see DNS requests for command and control servers. So if we have a list of either known CNC IP addresses or known CNC DNS names, we can find the clients that might be compromised that are calling out to those systems on a regular basis. We talked about tunneling already, but if we look through our logs and detect an abnormally high number of lookups for a single domain, that's going to be an anomaly. Normally, you're not going to see hundreds or thousands or millions of requests for very similar domains or subdomains on the same domain in a very short period of time. That would definitely be an anomaly that can be picked up and seen as something, okay, this client is likely doing some data exfiltration through DNS. Then we also have threat intelligence research, which the term that one of our level 3 analysts at Hurricane Labs, Tony Robinson, likes to use is guilty by association. He actually gave a really great presentation at Circle CityCon walking through how OSINT can be used, and some of this ties very nicely into what I'm talking about here. But really, this is the idea of using DNS data to determine IPs that are likely to host malware. And really, where other domains that are associated with a domain, or those IPs, they're just significantly more likely to also be malicious. So the way we look at this is, let's just start, we have this domain, baddomain.com, and any of the domains that are going to appear in here, they're not necessarily bad, I just made them up as being potentially bad. So baddomain.com might be a perfectly good site. You can check it out, if you get infected, I'm sorry. But obviously, we're going to know baddomain.com has an IP address that's associated with it. That is, your bad IP address. So let's look at other sites that clearly appear to be bad that are associated with that. We have, illegalcontent.com, phishingsite.com, exploitkit.net. All of these sites that tie back to this single bad IP address. But then let's start researching more domains that are associated with this IP address. So, like freesunglasses.com, for example. That could be tied back into this IP address. RussianWebs.ru, BreakingLabs.cn, cheaploans.com. All of these sites, they're not necessarily bad, but the fact that they're hosted on a site that's from a provider that has bad things there, they're more likely to be sites that are something that could be a threat. So it's a kind of a heuristic idea of identifying where clusters of bad stuff that systems might be going to, purely by using DNS data. And the way that we do a lot of the security and threat intelligence research is based on DNS logs. So the first thing you have to do in order to do this is to collect the data. Really, you want to have as much as possible your full DNS logs, which can be something that is a little bit of a challenge, but there's different techniques that can be used for that. A lot of times, if you're going to pull this in with like a Splunk forwarder, for example, your servers need to be in basically debugging mode or equivalent. A lot of times, your Windows admins are going to little balk about that because it's a lot of volume to be written to a log file, because there's constant DNS requests happening. Another option, and this ties back into the keynote earlier, the Splunk After Stream over the wire, where you can basically watch incoming DNS requests into your DNS server and immediately send that into Splunk for logging purposes. Now, my focus, obviously, at Hurricane is around Splunk, so that's what I'm most familiar with, but other SIMs have other ways for collecting this data. Just if you have any questions about that, I can definitely help you with the Splunk side, just I'm not as familiar about the other tools. And really the idea is once we get these DNS tool logs, we want to make them useful. So even if you're writing all your DNS logs to a flat file, you can't do a lot of the correlation, you can't do a lot of statistics on those logs. And that's really where a tool such as Splunk or another data analytics tool is really useful for understanding where are all my DNS requests coming from, what are the main sources of information, and how do I leverage that for security purposes. And really that's where the magic happens. There is so much information that can be gleaned from DNS results and DNS logs that it is one of the most important things when we're setting up a security solution for our customers that we want to make sure we have. Firewall logs, proxy logs, DNS logs, authentication logs, and a couple other sources of information can really help with making a security package that works well for our customers. So it would be amiss if I didn't just mention a little bit about what Hurricane Labs does, and then we'll open up the floor for questions. We do work as a MSSP, and we provide solutions in the area of managed SIEM, Splunk and SOC services. Those are our main tools that we use, Splunk being the engine that powers a lot of this. And then threat detection and vulnerability management. So with that, I want to open up the floor for any questions. Hopefully now that you know how at least part of the internet works, you'll be more empowered to do your job and do that. Yes?
So, best practice, how long do you keep the logs for forensics?
So the question was, what is the best practice for keeping the logs for forensics? That definitely depends. What I see drives a lot of that is retention periods for compliance. So a lot of people want to keep logs for PCI or whatever type of compliance purposes that you need, and that could be a year. That's a lot of data to keep for a year. So it really depends on the mean time for detecting something and the investigation time period. I find a lot of this is driven by alerts. So in some of the cases where you're going to see an alert pretty quickly and take action on investigating it, you don't need that long of a retention period. But then again, the industry average for finding an attack or something like this is something obscene like 6 months or years. So if you don't discover an attack until 6 months down the road and you don't have all that DNS data, you're not going to be able to have as good an idea what happened. So something like that Splunk, for example, if you dump that data to, just the compressed, unsearchable version and just archive it in like Amazon Glacier or something like that, that's really cheap to keep that data stored for a long period of time. You don't have to actively keep it searchable unless something comes up. So that might be an option for that. But generally, I see the year time frame as being a common compliance number. Any other questions? Okay, well, we'll throw up my contact information there. If you have any questions afterwards and want to chat, feel free to find me. I also have business cards here if you want to grab my contact information and follow up later via email. But thank you very much for coming. Enjoy the rest of the day and enjoy the conference.